Thank you very much for the invitation. Let me amend my title a little bit and make it into a question. What do modular forms with small Fourier coefficient know? Actually, we don't want to be that strict, just with small p Fourier coefficient. And actually only p Fourier coefficient whose p part is small. What do they know? That'll be the question that I'll be asking, and I won't be able to answer it. So the story begins with class numbers. If you're given a number field, so that there's a finite extension of Q, which is a field, then you can do arithmetic in this field. And one of the groups that knows the arithmetic a little bit is the class group. So that's the group of fractional ideals. And modulo the principal ideals. And the size of this measures how far you are from unique factorization. It is something we would like to understand. So just the number, not necessarily the group. Just to give you a flavor how hard this is. Let's look at the simplest non-trivial case, or so we think, right? So let's say case is quadratic. A quadratic extension. Well, so for example, you can look at the imaginary quadratic extensions. So Q adjoined square root of minus d. It turns out that if d is 1 or 2 or 3 or 7 or 11 or 19 or 43 or 67 or 163, then the class number is 1. But any other imaginary quadratic field has bigger class number. And to give you a sense of how hard this was, this was not known about half a century ago. If you look at Castles and Froelich, where I learned algebraic number theory from, they weren't sure if they were 9 or 10 still. So it's a very hard question. And the corresponding question is for real quadratic fields. And the unknown question is if there are infinitely many. With class number equal to 1. Unsolved question to this day, a question that Gauss asked. So what I want to say is this class number is hard. And since this was so hard, nobody in their right mind would really look at high degree extensions and try to compute class numbers. But then in 1956, Iwasawa came along. And he constructed an infinite tower of number fields and was able to say something about the class number. So he constructs, given some prime number p, an infinite tower of number fields, Qn. So those are extensions of Q. He constructed them so that the Galois group of Qn over Q is z modulo p to the nz. Very reasonable Galois group, not too hard. And by looking at all of these, in particular by looking at the compositum of these, he was able to say something about the class group. So the Galois group of the top guy is isomorphic to ZP. Let me draw you a picture of ZP. So ZP, the p-adic integers. This is a picture of the p-adic integers. Yeah, you have 0 inside here. You have 1 on the boundary. And then let me also draw you a picture of Z. That's Z. It's dense inside ZP. So by dealing with this slightly unfamiliar and weird object, he was able to say something about the class group. And here's his theorem. It says, if you look at the class group of Qn, and you look at just the p part, the p primary part, well, then the size is just the p power of whatever the size of the class group of Qn was. So let's denote this by p raised to the e sub n. We would like to know what e sub n is. His theorem says that for sufficiently large n, the difference between En and En minus 1 is equal to mu times p to the n minus p to the n minus 1 plus lambda for some constants mu and lambda which don't depend on n. So I'm not sure if n includes 0, so I think it differs from country. So let me be safe and write it as an n greater than or equal to 0. Great, so he came up with this theorem. You might ask, where do the invariants mu and lambda come from? Well, the answer to this question is that they come from a power series. So an element f inside a power series in one variable, where the coefficient ring of this power series is, again, this slightly weird group ZP. And it turns out that whenever you're given such a power series, you can factor this into a product of the form p to the mu times some monic polynomial x to the lambda, where the other coefficients are small. This g of x is a polynomial. This times some unit, which is an element of ZPX, but it's a unit. So somehow there's a power series f that knows everything about the class number, well, at least the p primary part of the class number, as soon as you climb up in this tower sufficiently high. So the moral was, there's this f. It knows the size of the p part of the class number. So one thing that had happened a few years earlier so before Iwasawa, Kubota and Leopold constructed a p-adic zeta function we call it zeta p-adic. And this zeta p-adic was constructed so that special values of the Riemann zeta function. So you're tempted to wonder whether these two functions are the same. And it turns out, this is the statement of the main conjecture, that f is equal to zeta p-adic times some unit in zpx. So that's the statement of the main conjecture in Kurosawa theory. It's now a theorem of Maser and Wiles. Great. So that's class numbers. So let me talk about something else, because the title contains the word modular form, and I haven't mentioned modular forms at all so far. Let's talk about Teichov-Hurwitz groups. So what are those? Well, this is a completely different story, so it seems at the beginning. Here's the beginning of the story. Let's look at an equation. It's called E in two variables. Y squared equal to x cubed plus ax plus b, where a and b are in Q, rational numbers. Well, this thing is called an elliptic curve, and we're interested in the rational solutions EQ, set of all xy and q squared, which are solutions. We would like to understand those, and this turns out to be very hard. In 1922, Mordell proved that this group of rational points of the elliptic curve has the structure of a finitely generated abelian group. So you can write this as a direct sum of some free part, z to the rank, and a torsion part. What makes EQ hard is that we don't really know the rank. So you might now just say, well, what if you just reduce the coefficients? So instead of looking at the solutions in Q, you look at the solutions over a finite field. If you reduce this equation modulo p, this works when p is a good prime. I won't explain what this is, but let me just say almost all primes are good. There's only finitely many bad primes. Well, it turns out that if you look at the number, the cardinality of this solution set, it's approximately equal to p plus 1. And the difference, a sub p, which is the difference between p plus 1 and the actual number of solutions, turns out to be small. So E of fp doesn't really tell us much about the rank directly. We can just cobble together these a sub p's and construct a complex analytic function that should know something about the elliptic curve, right? So you take these APs, you put them together in a certain way. Well, so this function, the L function of the elliptic curve, is conjectured to encode the value rank that I mentioned over there. And this conjecture is the Birch-Smerton-Dyer conjecture. And it states that this L function appropriately normalized, so just write down L function divided by C, where C is some product of certain algebraic invariants, which I won't define. And this is equal to the size of a certain group called the teacher of average group times s minus 1 raised to the rank plus a bunch of higher order terms. In the variable s minus 1. So s minus 1 to the rank plus 1 times some constant which is not specified. So I haven't really mentioned what this is. This is so it is the teacher of average group. It is an analog of the class group that I mentioned before. So it measures the failure of the local global principle. So the failure of getting global information just by looking at local points. It's presently not known to be finite, so it's a little weird that we have the cardinality of this group. So there we have it. We have an L function which is constructed from local data, and then we have terms here. One term encodes something global, and the other term encodes the failure of the local global principle. So this somehow should tell us everything we can about the elliptic curve. So you might wonder about the status, and if you're not a number theorist, please don't laugh. So this is how little we know. We know the following. So the first thing we need to know is the rank part. That's the famous part of the conjecture. So you want to know that the order of vanishing at 1 of this L function is equal to the rank, right? Unfortunately, this is not known at all. So here's something we know. So first part of the story was that if the value here is non-zero, so if the order of vanishing is 0, then the rank is 0. Well, if you combine the known results so far, we can only really say something about the rank 0 or 1 case. So let me write down the known results. We know that the ranks agree when they're low, and if you add the condition that SHA is finite on the algebraic side, not much is known. So this is the rank part of BSD. But we would also like to say something about SHA other than just that it's finite. So what about the SHA part? So one strategy to understand the size of this number SHA is to understand the p components, so the p primary components. So you want to understand the size of SHA And let's not be so ambitious. Let's just understand the P primary part. Well, so here's the idea that Maser had in the 1970s. Instead of just understanding SHA of E over Q, why don't we understand SHA of something much harder? So the SHA of E over Qn. So if you understand all of these, then maybe you can understand the size of SHA that we're interested in. So here's a theorem that Maser proved in the 1970s. So I think that's 1974. So assume that the P primary part of SHA is indeed finite. And also assume that this number AP is co-prime to P. And for sufficiently large n, we have a similar formula as in Iwasawa's classical case of class groups. I'm cheating a little bit here. I'm assuming some properties about the prime numbers. So let's assume all day that P is a good prime and bigger than 2. So where do the invariants mu and lambda come from? Well, it turns out that in the case where P does not divide AP, they again come from some power series F. Maybe let's call it F sub E to distinguish it from the number field case inside ZPX. You can relate this power series, which now should know the size of SHA for various Qn to the corresponding analytic function. We call it zeta E sub p-adic, because it's a p-adic function, which knows the values of, well, let me just say it knows analytic values of the elliptic curve. So let me give you an example. If you evaluate this function at x equal to 0, then this gives you the value of this L function at 1 times some normalization constant. So what's this main conjecture good for? Well, the idea is that if you take these two power series, the algebraic power series and the analytic power series, and you scrutinize their behavior at x equal to 0, you get something back. In the algebra part, you get back the size of the Chauffeur-Tate group over Q. And on the analysis part, as suggested by this equation, you look at what happens when x is equal to 0, you get back what happens to the L function, the complex analytic L function, when s is equal to 1. In particular, what you get is that the p primary part of this equality of the leading term is the same. So if you look at the leading term of this number, it should be equal to the leading term on the right side, which is the size of Shah. Well, this is a little bit too good to be true, but we want to at least know that whether the p primary part, so the p part of this, is the same. And it is the same if this equality is known. Right. So that's the idea when p does not divide AP. So now you might ask the question, well, what happens when p divides AP? Well, in this case, things become more complicated. But here's something. It's a continuation of this theorem of Mazur's. So in the remaining case, when p divides AP, it was actually quite mysterious what happens to the growth of Shah for a long time. So numerically, people computed it on the computer, and it seemed to grow much more rapidly. And finally, Kurihara came up with a theorem. He said under some assumptions, it's the corresponding formula is given by this term. It's the Kurihara term. You call it Q sub n. And then actually, let me call it Q sub n sharp. It's an alternating sum of p powers. So this alone indicates that the case where p divides AP is much more complicated. It's a bunch of p powers. Which depends on the parity n. So there's a corresponding term which is also p power, but which ends in p minus 1 if n is even. So Kurihara, under some assumptions, he proved that, again, for a sufficiently large n, en minus 1 is this term, qn sharp. Let's say for odd n, there's a corresponding formula for even n. And this is generalized. This is 2002. It was generalized by a bunch of other people, Kobayashi, Perrin Ryu. Over the years, it was generalized to to include basically all cases. 2003. It's more like 2012, 2013, something like that. And it states that En minus 1 in general is equal to this formula here. So some mu times p to the n minus 1 plus lambda star. Let me call this term q and star. So there's a similar definition for q and flat. And what this theorem says is that there's a pair of constants so mu sharp, mu flat, and another pair, lambda sharp, lambda flat, which are again independent of n, so that En minus 1 is exactly equal to this formula. But these indices depend on the parity of n. So for example, under the assumptions of Fourier, it was q n sharp for odd n. In the general case, there's an algorithm to determine which index you choose, sharp or flat. So those are mysterious constants, mu sharp, mu flat, lambda sharp, and lambda flat. So we can again ask ourselves the question, well, where do the constants come from? The origins of mu sharp flat and lambda sharp, lambda flat. It turns out they come from pairs of power series. So some power series F sharp associated to E and F flat associated to E. So again, they're the power series inside this slightly crazy ring, ZPX. And we can again formulate something that's a main conjecture. In fact, we have two of these, so we have a pair of main conjectures. For example, it says that Fe sharp should be up to a unit equal to a p-adic analytic counterpart of Fe sharp called zeta p-adic sharp. And similarly, Fe flat should be equal to zeta p-adic E flat. Maybe I should write sharp flat, sharp flat. And again, the same stream of ideas holds. If you scrutinize what happens at x equal to 0, then this should tell us what's going on with BSD. So we can conclude something like this. Maybe I should write down what the status of the main conjecture is. So the main conjecture holds. So in the classical case, when P does not divide AP, it was work of Rubin first. So it's proved under small assumptions. Rubin in the same case, and then Kato and Skinner-Urban proved the reverse inclusions to each other, so you get equality. And AP is 0, which is what usually happens when P divides AP. There's work of Pollock and Rubin in the CM case. And then Kobayashi was the one who formulated the main conjecture and proved one inclusion using work of Kato. And there's recent work of Shinwan. The remaining case concerns the prime 3 because of the Weil bound, and this can also be done. So basically I have this. So at the end of the day, we can say that the p primary parts inside BSD agree. So that's all nice, but where do we go from here? Well, one of the secret mechanisms that made all this work was that elliptic curves over Q. If you look at these elliptic curves, they secretly come from very symmetric functions called modular forms. Certain modular forms. So you can simply think of them as Fourier series. A sub n e to the 2 pi I n z dz. They don't come from all modular forms. They come from those modular forms, well, which first of all are of weight 2. It's one technical condition. And also, so that these Fourier coefficients a n r and z, there's some other conditions that it satisfies. It comes from a congruent subgroup. And now we've played this game with elliptic curves. We've estimated the size of Shah for elliptic curves, but you can equally estimate the size of Shah for modular forms. Let's step back a little bit. I'd like to point out that this AP here corresponds exactly to this, well, the P part of the P Fourier coefficient here. It's one of the nice parts about this correspondence. So this was the engine of Walter's proof of Fermat. So, as we should mention, Wiles, Taylor Wiles, and the work of Breuil, and Conrad, and Diamond, and Taylor. So now we can ask ourselves the question, what is Shah equal to, the size of Shah equal to, when, let's say, the weight is still 2? But A sub P is not in Z. So this, you can again define a Tate-Fourier group for this modular form. Let's call it G over Qn. You want to look at the P part of this. So what is this? What is En minus 1 equal to for large n? Well, and the answer to this turns out to be very weird. And that's actually the question I have for this talk that I'm not really able to answer. So let's rewrite AP, which is now not necessarily an integer. You can write this as a power of a prime, write it as p to the v times some algebraic integer that's co-prime to p. So for example, if you look at the case where p does not divide AP, back in the case where AP was an integer, this would be the same thing as saying that v is equal to 0. That way you have two to integers or numbers that are co-prime to P. When P divides AP, it's the same thing as saying that V is bigger than 0. And saying that AP is equal to 0 is the same thing as saying that this V is equal to infinity. So this, what I'm up to is, I'm about to give you a formula for SHA, which only depends on V.
So give chosen the place above P the number V headed by the coefficients.
Say it again?
You've chosen a place above P.
Yes, yes. I've chosen it, and I didn't tell you about it. It's a secret. Yeah. So there's one place above.
You assume one place?
We've chosen one place. Above P, yeah. It doesn't matter which one you choose. Yes. So now, what is En minus 1 equal to? Well, the answer turns out to be extremely weird. So recall that I've drawn a picture of the p-adic in a disk. So let me draw it again. I will need this formula. I will need that formula as well. So recall we're in the weight 2 case, but AP is not necessarily an integer. Well, draw the p-adic in a disk again. So this is ZP. And let's think of where AP can be. The center is where AP is equal to 0. So in other words, as we saw over there, this number V is equal to infinity. On the boundary, you call that the point 1 is somewhere here. On the boundary, AP is co-prime to P. So V is equal to 0. And in between, V is between 0 and infinity. Now the theorem says the following formula holds. So the let's just say for odd n, the formula for En minus En is this one when you are on the boundary. It's like when you're somewhere here. When you're at AP equal to 0, so at V equal to infinity, it's this formula here. And it turns out that this formula remains true if you're in a small region around the point AP equal to 0. So as long as V is bigger than 1 over 2P, this formula holds. For odd P, for odd N, we choose the sharp invariance, not the flat invariance. Let's say V is at least 1 over 2P. So you're inside this disk anywhere, so not necessarily at 0, but anywhere in here. Then this formula holds.
Does P have valuation 1?
I'm sorry?
Does P have valuation 1?
Oh, yes. Yeah. So you basically can deform this formula and make it hold inside this unit disk. Now, the punchline of this theorem is that there's a bunch of formulas which get very complicated, so let's just assume that any term that involves mu is 0. So that mu and mu sharp and mu flat are all 0. When they're not 0, I've simple formulas, but let's just, for now, for simplicity, assume that mu is 0. So this goes away, and this goes away. So in particular, the growth of sharp is just given by lambda when you're on the boundary, and by the sum of a lambda invariant lambda sharp and the Fourier term qn sharp when you're inside this close to 0. Well, it turns out that if you look at an annulus, where v is between 1 over 2p squared and 1 over 2p. And inside here, something really weird happens. So recall we're looking at odd n. I should also say n is sufficiently large. If you look at odd n, well, you expect that this formula should hold. But it turns out that for some reason it's the other pair, the other invariant that comes into play. So it's lambda flat plus a similar term to the Fourier term, qn flat. But it's not quite this Fourier term, but a Fourier term that's been slightly modified. So this term, which is big when p divides ap, becomes modified. So instead of this term, you have a slightly smaller term. And well, the story continues. So you can then after that look at another annulus. If you look at the next annulus where this v is 1 over 2p cubed. If v is between 1 over 2p squared and 1 over 2p cubed, then the formulas for the growth of sharp are lambda sharp plus qn 2 sharp, where qn 2 sharp is another term like this. So instead of 1, you have 2. And something like this. So the number v starts eating away at the alternating p power sum. My question is, where does this phenomenon come from? This is completely weird. Why this should be happening? It continues. So if you look at the next annulus, what happens is that the sharp becomes a flat, and this term qn, which is an alternating p power sum, becomes even smaller. So in the next annulus, the term p to the n minus 5 minus p to the n minus 6 gets eaten. So infinitely many more formulas like this. And I have no idea where these formulas come from. Right. So this is the weight 2 case. You can now ask, what happens when the weight is higher? So what if the weight of this modular form G is even higher? So we're getting farther and farther away from the world in which the modular form comes from an elliptic curve. So let's say the weight is equal to some integer k, which is not necessarily true. Not necessarily 2, but greater than or equal to 2. Well, the answer in this case is that there's a theorem of Ley, Loeffler, and Serbus, which says that the difference en minus 1 is bounded above by a formula of this form. formula of the form, and the last row. And they're able to do this as long as V, again, is inside some small disk. It depends on the weight. So they're able to give an inequality in this case. And very recent work of Otsky and myself shows the following thing. So Otsky constructs these p-adic sharp and flat zeta functions when basically when k is less than or equal to p, and so this can also be done for all k. The constructions are different. But it'll be a joint paper. But the application of this is that we can compute these candidates for en minus 1. They behave equally crazily in the higher weight case. So there's equally complex zoo of formulas. As in the case when the weight is equal to 2. So I've asked a bunch of people where they think this phenomenon comes from, and nobody, especially the number theorists, have been able to give me any sort of satisfactory answer. So if you have any idea with any other field of math or life, where you've seen something like this, please let me know. That's it.